If you're getting ready for your nursing exam, you know that fluids and electrolytes are a huge deal. I mean, they're involved in pretty much everything. So in this explainer, we're going to cut right to the chase and focus on the absolute must-know stuff that's going to help you nail your test.
So, let's start with a big question. What is the body's most critical balancing act? Well, every single second, our bodies are in this constant, really delicate dance to keep everything in perfect equilibrium. And if you can understand that balance, you're going to understand everything else we're about to cover.
Okay, here's our game plan. We'll kick things off with the basic rules of how fluid moves around. Then we'll jump into the big imbalances, really focusing on how potassium messes with the heart and how sodium messes with the brain. And then we'll finish up with the other key players you gotta know.
All right, first up, the foundations. Look, before we can get into what goes wrong, we have to know the rules of the game, right? We need to know who the players are and what forces are pushing them around inside the body.
So what even is an electrolyte? Well, think of it like this. It's a tiny little particle with an electrical charge. When these things dissolve in our body fluids, they basically turn that fluid into a conductor for electricity. And that electricity powers, well, everything, from your heart beating to your nerves firing.
And these charged particles come in two flavors. You've got your positively charged ions, which are called cations. A really easy way to remember this is to think of a cat. Cats have paws, so cations are positive. Cheesy, I know, but it works. Anions, then, are the ones with a negative charge.
Okay, this is so important to visualize. Where does all this fluid actually live? A whopping 70% of it is intracellular. It's inside our cells. Only 30% is extracellular, hanging out in our blood vessels and tissues. Getting the 70-30 split in your head is absolutely key to understanding why fluid shifts happen the way they do.
So, what makes all this fluid move? The main force is osmosis. And if you remember one thing from this whole section, make it this. Water always follows the solutes. It's always trying to move from a weaker, less concentrated area to a stronger, more concentrated area to try and dilute it. That one simple rule explains pretty much every fluid shift we're about to talk about.
So let's put that into practice. What happens when the body's total fluid tank is either running on empty or it's overflowing? This is where we get into fluid volume deficit and fluid volume excess.
So here they are, side by side. On one hand, you've got fluid deficit, or dehydration. This is usually about losing fluid faster than you're taking it in. The goal? Super simple. Get more fluid in. On the other hand, you've got fluid excess, or overhydration. This is often because the body can't get rid of fluid, like in kidney or heart failure. So the goal here is the opposite. Help the body ditch that extra volume. Now, let's talk about what you'll see. For your exam, I want you to zero in on those cardiovascular findings. With a fluid deficit, think about it, there's less volume in the pipes, right? So the pulse gets weak and thready and the blood pressure drops. In fluid excess, there's too much volume flooding the system, so the pressure shoots up and the pulse feels strong and bounding. That contrast is a classic test question. And check out the labs. In a deficit, everything gets concentrated, so the numbers go up. In excess, it's all diluted, so the numbers go down. Makes sense, right? All right, let's dive into our first superstar electrolyte, potassium. If you remember one and only one thing about potassium, make it this. Potassium is all about the heart. The heart's electrical system is incredibly sensitive to even the tiniest changes in potassium.
And here it is, an absolute must-know number for your exam. I mean it. Write it down, burn it into your brain. The normal potassium level is 3.5 to 5.0. Going outside this super narrow window is a huge deal and can be life-threatening.
Now, here's where it gets a little tricky. Notice that both low and high potassium cause muscle weakness and an irregular heart. So how do you tell them apart? Well, the GI tract gives you a clue. Low potassium slows everything down, causing constipation. High potassium speeds things up, causing diarrhea. But the real, definitive answer? You're going to find that on the ECG. And these are the ECG fingerprints you just have to know, period. For low potassium, hypokalemia, the dead giveaway is that prominent U wave. For high potassium, hyperkalemia, the classic hallmark sign is those tall, peaked T waves. Being able to spot these on an exam is an essential skill.
Okay, everybody listen up. This is a critical safety rule, one of the most important things you'll ever learn. You never, ever give potassium as a direct IV push. It is lethal. It will stop the heart. IV potassium always has to be diluted and infused slowly on a pump with careful monitoring. No exceptions.
All right, let's switch gears to our next big player, sodium. So if potassium is all about the heart, sodium is the chief conductor for the brain and nervous system. When you think sodium, I want you to think neuro.
And you guessed it, here's your next must-know value. Normal sodium is 135 to 145. It's a bit of a wider range than potassium, but our bodies still keep it on a very tight leash. The number one thing to get here is that both low and high sodium cause major changes in the brain. Look, confusion and seizures are on both sides of the chart. So what's the why behind this? Well, remember our rule. Water follows solutes, and sodium is a major solute. So in hyponatremia, when sodium is low in the blood, water rushes into the brain cells, causing them to swell. In hypernatremia, when sodium is high, water rushes out of the brain cells, causing them to shrink. Either way, you're disrupting brain function, and that's really, really dangerous.
All right, let's wrap this up with the supporting cast. Calcium, phosphorus, and magnesium. Yeah, sodium and potassium get all the attention, but these three are absolutely critical for things like muscle contraction and nerve function.
You know the drill by now. Here's your next must-know number. The normal range for calcium is 9.0 to 10.5. And remember, calcium is a workhorse. It does everything from keeping bones strong to helping blood clot and muscles contract. This slide shows two signs you absolutely have to know for low calcium, or hypocalcemia. On the left is Trousseau's sign. You inflate a blood pressure cuff and the patient's hand cramps up. On the right is Chapt's sign. You tap on their facial nerve and their face twitches. So why does this happen? Well, low calcium makes the nerves and muscles super irritable and easy to trigger.
Now, this is a key relationship you have to lock in for your exam. Calcium and phosphorus have this inverse relationship. Just picture them on a seesaw. When calcium goes up, phosphorus goes down. When phosphorus goes up, calcium goes down. They're always moving in opposite directions.
And finally, magnesium. Here's the easiest way to remember this one. Think of magnesium as a sedative, like a chill pill for the body. The more magnesium you have, the more chilled out and sedated everything gets. So low magnesium, or hypomagnesemia, makes the body hyper and excited. You get hyperreflexia, a fast heart rate, high blood pressure. High magnesium, hypermagnesemia, does the exact opposite. It makes everything slow and sluggish, with diminished reflexes, a slow heart rate, and low blood pressure.
Okay, and that brings us to our final thought. Let's try and connect all the dots. Think about this clinical question. The kidneys are the master regulators of pretty much all of this stuff. So when they start to fail, which electrolyte imbalances are you going to be on the lookout for first? Answering that is what this is all about. Thanks so much for joining this explainer.